Welcome to the Introduction to Schematic-Driven Design, where we discuss advanced design methodologies. This design methodology mirrors what is done in electronics, namely where most of the design time is spent on the abstract schematic and circuit simulations as opposed to physical component modeling and layout. This approach is critical to develop large-scale silicon photonic systems and to move the field beyond individual components. We begin this section with a discussion of how VLSI CMOS electronics design is done. In summary, we are trying to replicate what the electronics world has been doing for many years, using what is known as electronic design automation, or EDA, using a mature process design kit, or PDK. We will talk about who will develop this PDK, and finally, we compare the bottom-up approach by which we began this course, where we focused on the physical modeling, to the top-down design approach, where we focus on circuit design. Let's discuss how the electronics industry designs chips containing billions of transistors. This is called Very Large-Scale Integration, or VLSI. The key innovation was the separation of process and design. The foundry takes care of the technology, which is dominated by CMOS, or complementary metal oxide semiconductor. They take care of developing devices such as transistors and resistors, fabricating test structures, characterizing their performance, and building these device models. The designers don't worry about the device details, but rather focus on circuit design. The communication between process developers and circuit designers is via process design kits, or PDKs, which are provided by the foundry. The designer, in turn, submits a layout for fabrication. So imagine how easy it would be to design a Mach-Zehnder interferometer if we had such a mature separation. We would just need to create a schematic, simulate and lay out the circuit, and not worry about the physics and modeling of the components like the waveguides. So what is the Process Design Kit, or PDK for short? It is a collection of data embedded within software tools. Of course, there is extensive documentation detailing the fabrication process parameters, the rules, a layer table, and details about the devices in the library. In a mature CMOS process, the documentation is typically thousands of pages long. The PDK contains a library of components which includes models. These are compact models created using empirical expressions with parameters extracted from experiments. The components all have physical layouts. With the above, the PDK allows for a design flow that consists of several key steps. We will go through the main ones in more detail later. The steps include schematic capture, circuit simulations, schematic-driven layout, or SDL, design rule checking, DRC, layout versus schematic, LVS, and other functionality such as routing, design for manufacturing, or DFM, lithography simulation, including optical proximity correction, or OPC, and design for test, DFT. Now, this is a long list of capabilities which has taken over 30 years for the industry to develop. All this is called Electronic Design Automation, or EDA. Let's see how this compares to where photonics is and see the evolution of photonics design methods. First, let's examine the simplest design methods. Here, everything is done mostly manually by hand or with your own scripts. For example, the waveguides are created by hand and consists of polygons. There's a small number of components consisting of GDS layouts. There's some documentation. Circuit modeling is possible, but can be challenging. Most of the effort is aimed at designing individual components. Finally, error checking is challenging. Checking for fabrication design rules is generally straightforward, but checking to ensure that your circuit has the correct behavior based on your design intent is not easy. What we've described is typical for a university research effort. Now, let's see where photonics is going. The design methods will be similar to electronic design automation with comprehensive process design kits. We will have a mature component library, circuit simulations using compact behavioral models, schematic-driven layout, extensive DRC, LVS to ensure that the physical layout matches the schematic, and simulations will include the manufacturing variability and yield. The first comprehensive EDA-style PDK was developed by Luxtera and used to commercialize silicon photonic transceivers. Having a complete PDK is ideal for the fabless model, where companies work on the design and the foundries do the fabrication. So what we require for silicon photonics and is happening already, is similar to electronics, namely the separation of the fabrication process and the circuit design. What isn't totally clear is who will develop the PDKs for silicon photonics. Silicon photonic foundries are gradually starting to develop PDKs, but they are still immature compared to the electronic PDKs we have described so far. To date, most of the companies and researchers working in silicon photonics have had to develop their own PDKs, or at the very least expand upon them to build what they want. It has been seen as a necessary evil and an inefficient use of everyone's time. Design tool vendors have an interest in helping the community, so they are helping develop the PDKs, particularly in the early days. Next, we have the multi-project wafer aggregators such as EPICS-Fab in Europe, CMC Microsystems in Canada, or Moses in the United States. Finally, we have third-party library providers. In CMOS electronics, there have been several companies that provided libraries, so a similar opportunity exists in photonics. In a sense, the SciEpic program has been in this category as an academic effort to develop PDKs and libraries. Let's turn our attention to the future design flow for silicon photonics. Here, the design flow starts with a circuit schematic. We call this a top-down approach. We begin with symbols for the components and place them on a schematic. This allows us to immediately simulate the circuit. As you'll see, if you've done this once before, it only takes 5 minutes to get to the point where you have a circuit simulation. Behind the scenes, there are already developed component models. You don't need to develop them yourself since they are provided in the PDK. More advanced PDKs and processes will include active optical components and perhaps electronics. In this flow, the layout is created on the basis of the schematic. The software actually helps you with your layout by reading the schematic as you perform your layout and knows about how the components are connected. It's quite fun, as you'll see. The verification step is now more sophisticated. Because you have a schematic and a layout, we have the opportunity to compare them. In fact, there is a tool and a set of rules called Layout versus Schematic, or LVS. LVS looks at your layout, recognizes the components, and compares the components and connectivity with the original schematic. The rest of the flow is the same, namely fabrication by foundry, followed by testing and packaging. The main difference is that this design flow has a much more well-established PDK and enables rapid design of complex circuits without having to spend time on modeling individual components.